Okay, hi. This is a new lab we're trying out for the first time this year, and what we're going to do here is look at some basic optics. We're going to use a little laser and a glass full of water and a few lenses and do some basic optics experiments. The first thing we're going to do this week is look into reflection and refraction. Okay, so the first thing is reflection. And reflection is what happens when you have a smooth, flat surface like a mirror or the top of a glass of water or something. And what happens here is that a light ray comes in and goes out again. And the physics involved say that when that happens, the angle coming in, theta incident, is equal to the angle going out. Off that way. So this is theta reflection. And this is what happens on any smooth surface. We're not bothering about what's going on underneath at the moment, and we'll look at that. The other thing that happens is refraction. And with refraction, you have once again a smooth surface, but now we do worry about what goes on underneath. And what goes on underneath depends on something called the coefficient of refraction of the two surfaces. It's generally known as N. I'm just going to call this N1 on top and 2 on the bottom. Different materials have different coefficients. If you have a light ray coming in and hitting on here, you still get a reflected ray, which works the same way as it did over there, but you also get a refracted ray. And the refracted ray goes at a different angle. And the way it works is that if you take that times the sine of the angle on one side, and that will equal this times the sine of the angle on the other side. So theta 2 in here is so. And what this generally means, usually you have a situation where you have something like air and water. N for air is basically 1. Ed for water is greater than 1. And what that means is that the angle in water is smaller than the angle in air, so you get a kind of a dog leg. The light ray comes in, hits the surface, and then bends as it goes down. And we'll have a look at that in a minute when we get out our lasers and a glass of water and start exploring this. All right, now it's time to actually do some experimenting. What I have here is a glass of water, and I have a laser that I got from Office Depot. It's just a cheap little laser pointer. All right, so to make this more visible, we're going to add some cream. This is just basic half and half to a glass of water, and stir it up. And we'll get just a few drops. You really don't want to overdo it. And then stir it up. You want the water to get a little foggy, but definitely not opaque. Stir it up good. And when you get done, if you shoot the laser to it, you should be able to see the beam in the water as it goes through. And I can see it in there. Okay, here's the first thing we're going to do. It's easier, actually, to see what's going on if you shoot the laser beam in from below and bounce it off the top of the water. And if you're looking from above, you can see the entering laser beam in the foggy water, and you can see the exiting beam as it bounces off the top of the water, off the water-air interface, and continues down through the water and then comes out. And the exiting laser beam is right here on the tabletop. And I don't have a way to precisely measure it, but I certainly would believe that the angle going in is equal to the angle coming out, and thus we have reflection. The angle on bouncing off this top surface is the same coming in and going out. If we look at it from the side, you can see it. The interesting thing is the refractive business. If you shoot it straight in from right above, it continues straight down, and you can see that it's doing that. But as you increase the angle, so as you move your hand off to the side, the angle the laser makes in the air is quite a bit more than the angle it's making in the water. In other words, this angle is much bigger than the angle down in the water. This is refraction. Refraction is what happens when a light beam goes from one medium to another with a different index of refraction. And if you move the beam around, this is actually fairly clear. As you get to bigger and bigger angles, the refraction in the water becomes quite clear. Eventually, you come to a very interesting situation in which the angle in the air is 90 degrees. And you can approach that from below or from above. You bounce it off from below. We're going from high index of refraction to low, so the refracted beam is bent over more. And eventually you get to the point where the ratio of the two index of refractions are such that the angle in air just can't bend over anymore. And at that point, the refracted beam in the air vanishes. And at that point, all the light is being bounced off in the reflected ray off the surface. This is known as total internal reflection. It means that there's no leakage. The light does not leak out of the water. It all stays in the water. And if we had, instead of just a glass, we had a long pipe of water, this laser beam would stay completely in the pipe. It would never come out. You can, in fact, send lasers down streams of water. We have a video of that connected to the course. And this is how fiber optics work. Fiber optics send signals enormous distances by relying on total internal reflection. The beam you start at one end goes all the way down to the other and doesn't come out, even though the actual fiber optic is just very thin. It's, less than a centimeter. This is something I hardly encourage you to have a look at and to experiment with. It's actually really cool, and you get to play with lasers. Okay, well, that's it for the refraction lab. The next one we're going to do is about lenses and geometric optics. We will have you build a little tiny telescope and use that. Okay.